Hello, in this video we discuss law of iterated expectations and law of total variance. Remember that the expected value of a random variable x, if x is discrete, is equal to sigma xi px of xi, where the sum is over all possible values of the random variable x. And in previous videos we discussed that if I have a conditional expected value of x given y equals yj, where y is another discrete random variable, basically we use the same formula. The only difference is that the probabilities now are conditional probabilities. So we replace probability mass function with the conditional probability mass function of px given y of xi given yj. So the same idea is true about the variance. If I'm interested in variance of the random variable x, given that I have some additional information, in particular if I know the value of the random variable y is equal to yj, I can write this as expected value of x squared given y equals yj minus, so the same formula. The only thing is that now we are conditioning on y equals yj, and we can simply write this as sigma xi squared px given y. Again, note that I'm using the conditional probability mass function. So this is again just a conditional expected value, which I mentioned here. So basically I just replace it by px given y xi yj, the whole thing square. Okay, so we know how to calculate conditional expected value and conditional variance. In this video we want to go a little deeper, and we're going to introduce a notation that is sometimes confusing to students, but actually if you learn it, makes your life a little bit easier when you are working with these conditional expected values and conditional variances. In particular, the main idea here is that we are looking at the conditional expected value as a random variable. So what do I mean by that? Well, let's again look at the formula for conditional expected value. If you look at this formula, you notice that the value of this sum depends on the value of the random variable y, right? If I change this y, the conditional probability mass function changes, and of course I get a new value. So in other words, the whole thing is a function of the value of the random variable y. So the value of this sum may turn out to be something like, I don't know, maybe 3y squared plus y minus y cubed, or something like that, right? So in fact it's a function of y, so I can basically write this thing as the function of a random variable y, right? I can write that g of y is equal to 3y squared plus y minus y3. So the whole thing is a function of this random variable y. So I can write it as expected value of y, expected value of x given y, and this is some random variable, right? Because y is a random variable, a function of y is a random variable. So I can look at another random variable z, which is a function of the random variable y. In other words, I can have a random variable z, which is defined as expected value of x given y. How do I know the value of z? Well, the value of z depends on the value of the random variable y. So if the random variable y becomes y1, then the value of the random variable z is equal to expected value of x given y equals y1. In other words, z is equal to this term with probability py of y1. So we are looking at the conditional expected value as a random variable. To better understand this, let's look at an example that actually we discussed last time, or in one of the previous videos. So suppose that the number of customers visiting a fast food restaurant in a given day is given by a random variable n, which is Poisson with parameter lambda. And we assume that each customer purchases a drink with probability p independently from other customers and independently from the value of n. And x is the number of customers who purchase drinks, right? So we are interested in this random variable x. So basically x, given that n equals n, is a binomial random variable with parameters n and p. Why? Because if n is fixed, if the number of customers are fixed, then each customer, it looks like each customer tosses a coin with probability p, decides to purchase a drink. So we are, it looks like we are counting the number of heads, where p is the probability of heads in the coin toss, and in that case, we are counting the number of heads in a fixed number of coin tosses, so x is binomial with parameter n and p. So as we discussed last time, expected value of x given n equals n is the expected value of binomial random variable np, right? However, this is the conditional expected value. The value of the conditional expectation depends on the value of the random variable n. So if I change this n, the value changes. So in other words, I can write expected value of x given n. It's a function of the value of the random variable n, so it's equal to n times p, right? So it's another random, this is my random variable z, right? It's another random variable whose value depends on the value of the random variable n. So as I said, this is basically a kind of a new notation, no new idea, but basically we are using a new notation, and it's useful to kind of get comfortable with this notation. For example, here I want to discuss this rule that sometimes is stated as taking out what is known. Basically what it says is that suppose that I am looking at the expected value of x times y given x equals x, right? If I know the value of the random variable x, basically this x is no longer a random value, it's just, the value is just x. So I can take it out, so it's equal to x times expected value of y given x equals x, right? So if I want to use my own notation that I introduced here, basically I can write that I say expected value of x times y given the value of the random variable x. Because x is known, I just take it out of the expected value. So it's equal to x times expected value of y given x. And more generally, I can replace this x and y with a function of, gx times g of y. So this is called taking out what is known. So if I am looking at the conditional expected value like this, note that this is a conditional expected value, so it's a random variable, like again, random variable z, something like that. And then because I know the value of x, the value of g of x is known, so I just take it out of the expected value. Having discussed all of this, let's look at the law of iterated expectation, which is nothing but the law of total expectation that we discussed in previous videos, but it's just using the new notation. Remember, the law of total expectation, we mentioned that if you are interested in the expected value of the random variable x, you can write it as sum of ex given y equals yj, py of yj, when the sum is over all possible values of y, right? Now, if you think about this thing here is a function of yj, right? As we discussed. Now, I have the sum of g of yj times py of yj, which, by Lotus is just expected value of g of y, right? But g of y is nothing but, using our new notation, note that g of y is just expected value of x given y, right? G of y is this thing. So this is expected value of the expected value of x given y, right? This is just writing the law of total expectation using our new notation. And because you are taking two expected values, it is called the law of iterated expectation. So let me summarize it here. Expected value of x is equal to expected value of the expected value of x given y. Note that this thing in the middle is our random variable z, right? It's a random variable. It's a conditional expected value. It's a random variable, so I can take another expected value. So to summarize, law of iterated expectations can be stated like this, and it's just another way of writing the law of total expected value, or law of total expectation. So to get some more practice with our new notation, let's look at this example that we discussed last time. Again, the number of customers who are purchasing drink and so on, the thing that I just discussed it. And suppose that we are interested in finding expected value of x. Remember, expected value of x given n we found above, which is equal to n times p, right? We just found it. Now, if I'm interested in expected value of x, which means that the expected value of the number of customers who purchase drinks, I can just apply the law of iterated expectation, right? So this thing is equal to np, so I'm looking at the expected value of n times p. Note that p is just a given number, right? The probability that the customer purchases the drink. So there is nothing random about this p. So this is just p times expected value of n, and n is Poisson parameter lambda, so this is p times lambda. And we found this value in a previous video when we were talking about law of total expectation. As a special case, when we are looking at independent random variables, if x and y are independent, well, of course, we expect that the conditional expected value is equal to the expected value of x, right? Knowing the value of y doesn't change the expected value of x. So that's quite intuitive. Or expected value of any function of g, x, any function of x is again just expected value of that function. So another useful rule is that expected value of xy is just ex times ey. So again, this is true for independent random variables. More generally, if you multiply two functions of two independent random variables, then you can find the expected value simply by multiplying the corresponding expected values. So now let's talk about conditional variance. Remember, again, as I said, variance of x given y, you can write it as expected value of x squared given y minus ex given y equals y, the whole thing is squared. But note that here we said that expected value of x given y is a random variable, right? That's what we discussed. So similarly, variance of x given y is also another random variable. Why? Because its value again depends on the value of the random variable y. So we can look at this thing also as a random variable. So, and one interesting result that is true, in fact, we can show that variance of my random variable x can be written as the expected value of this random variable v plus the variance of this random variable z. And this is called law of total variance. So let's quickly prove it. First, note that using the law of iterated expectations, expected value of z is just expected value of the expected value of x given y, which is equal to expected value of x. Again, this is just law of iterated expectations. So z has the same expected value of x. So let me just rewrite things in a nice way. So z is equal to expected value of x given y, and we know that expected value of z is equal to expected value of x, and v is equal to variance of x given y. So z and v are two random variables. Now, note that I can write v as expected value of x squared given y minus e of x given y squared. Again, this is just a definition of conditional variance, right? However, this thing, ex given y, is by definition the random variable z. So this is just the random variable z squared. So let me just rewrite it here, ex squared given y minus z squared. So if I want the expected value of the random variable v, I just take the expected value of these two. But note that using the law of iterated expectation, I am taking two expectation. So this is just simply expected value of x squared, right? This is just by law of iterated expectations, and minus expected value of z squared. So remember, variance of z is always equal to e of z squared minus e of z squared, which is equal to e of z squared minus, remember z and x have the same expected value, ex squared. So I can replace this e of z squared here by variance of z plus e of x squared. So minus variance of z minus e of x squared, and we are done. So what is this? This is note that we are calculating the expected value of v, right? This we found it to be equal to, if I look at these two terms, this is variance of x minus variance of z. In other words, I have shown that variance of x is equal to variance of, or you can write it as expected value of v plus variance of z. And remember, v was this, conditional variance, and Z was conditional expected value. So the law of total variance, this is called the law of total variance. Let me just write it again. Variance of x is equal to expected value of variance of x given y plus variance of expected value of x given z given y. So the law of total variance says that variance of any random variable x can be written as the expected value of the conditional variance plus the variance of the conditional expected value. So this is called the law of total variance or variance decomposition formula, and we're going to look at an example that we're going to use everything that we learned in this video to kind of practice all of these concepts. So the example is this, very similar again to the example that I just discussed, but this time I want to find both expected value and variance. So n is the number of customers that visit a certain store in a given day, and suppose that we know expected value of n, variance of n. In the previous example, we assumed n was a Poisson random variable. Now we say we don't know the distribution of n, but we know its mean and its variance. And this is maybe in a practical scenario, you might not be able to find the distribution of n, but you can find the expected value and variance using just by observing in a certain number of days and find these values empirically. So anyway, we are given these two values, and xi is the amount that the ith customer spends on average. So this time we are looking at how much the customer spends, right? And we assume that xi's are independent of each other and also independent of n. We further assume that we have this, xi's have the same mean and the same values. So xi, each customer who enters the store spends on average this amount of money, and the variance of xi is given to be variance of x. So again, these two values are given to us. So we can assume that this is mu, right? This is equal to sigma squared, and mu, sigma squared are given. And of course, you are interested in the total sales, right? The total sales is given y equals sigma I from 1 to n xi, and our goal is to find expected value of y and variance of y. So my suggestion is that you stop the video and solve this problem using the stuff that we have seen in this video, in particular law of iterated expectation and law of total variance, and then watch the rest of the video. Okay, let's look at the solution. So we are interested in the expected value of this random variable y. Y is a sum of n independent random variables xi, but note that we cannot use the linearity of expectation here directly, because n is also random. We have a random number of x, and because the number of customers is random, we have a random number of random variables xi. So we cannot use linearity of expectations directly, but we can condition on n. So we know that if we know the value of n, right, then n is just y is the sum of n independent random variables. So its expected value is just expected value of x1 plus expected value of x2 plus expected value of xn. And note that xi's are independent of n as well. So this is, and because they have the same expected value, this is just n times expected value of x by the assumption of the problem. So what do? We use the law of iterated expectation. I'm going to write expected value of y is the expected value of the expected value of y given n, right? This is equal to expected value of n times e of x. Note that e of x is just a constant, it's just a value number, it comes out of the expected value, so it becomes e of x times e of n. So we have obtained expected value of y is equal to expected value of x, expected value of n, and both of these numbers are given in the problem statement, right? We know the expected value of n, we know the expected value of x, so we are done with finding the expected value of y. For variance, what do? We use the law of total variance. Variance of y is equal to, by the law of total variance, expected value of the variance of y given n plus variance of the expected value of y given n. So note that expected value of y given n, we found it is just n times e of x, right? So this thing is equal to, again, note that E of x is a constant. Remember variance of ax, where a is a constant, is just a squared variance of x, right? So in this case, I can variance of n times E of x, right? So let me just write it in a cleaner format. So this is equal to variance of n times E of x is equal to ex squared variance of x. So this term, we know what it is. So we need to find this term. So note that given n, y again is sum of n independent random variables which are independent of n, which means that their variance is the sum of their variances. So variance of y given n is simply sum from I from 1 to n variance of xi, and again this is given in the problem. This is, variance of xi is just equal to variance of some x. It's a given value. So this is just n times variance of x, right? So let's rewrite this here. Variance of y is equal to expected value of n times variance of x plus expected value of x squared variance of x. And variance of x again is a constant, becomes variance of x times expected value of n plus expected value of x squared times variance of x. And we are done. So that is the final answer. Variance of y is given by variance of x times expected value of n plus expected value of x squared times variance of x. Thank you.